Hello.
Can you hear me?
Hi.
Hello, hello. Yeah, I just got off of a session, so that's why I started a little bit late. But we could end at like 10:06 or something around that time.
Right.
Hello? Hello? Can you hear me?
Yeah, we can hear
Yeah.
you.
Yeah. Uh-huh.
I had discussion today, and then my TA said that, the table you said where fluorine is like primary, or like it
Mm.
wants to go to primary, they said that all of them should want to go to the one with 3 carbons.
All the 1, 2, 3 carbons.
Yeah, like fluorine, chlorine, and bromine.
Yeah,
You know how there's a table you made yesterday?
yeah. The general table that's not always the case, but that general table, yeah, that mostly works.
Yeah, Cam said that it should like all of them should go to the like the one with 3 carbons.
All of them?
That's what he said. Or all of them should want to go to there.
No, it's just
Recording in progress.
bromine. It's just bromine that wants to go there.
Okay.
Yeah, yeah. Fluorine wants to go to primary, chlorine wants to go to secondary, bromine wants to go to tertiary.
Okay.
Yeah. Okay. Let's see. Are there any questions that you guys? Oh, it's true. I see your guys.
I uploaded some problems regarding like nomenclature, like some of the harder problems.
Nomenclature. Okay, yeah. Let's try that. Let's see. Yeah.
And then there was like one where it was in Newman projection form as well. And I think I know how to draw it out. I kind of have a hard time drawing it in bond line form and then naming it.
Mm-hmm. Let's see. Yeah, class resources, practice problems, October 17th. Let's see. Okay. Just part of that.
And I have a quick question.
Yeah.
So like for ones that are like not halogens, right? So like there's some on the exams that I'm not sure if they're like ones that we should also know, like NaSCH3
Uh-huh.
or like um I guess like where it has like where it's above the arrow. I'm just like not sure how to go on by doing those. But like are those ones that we should also know?
Oh, are those the questions that we went over last night? The NAS and acid base reactions?
Um I don't think so. These ones are like relatively like it's from a different
Uh-huh.
practice exam. I think it's like midterm two.
Yeah. Let me see. Let me check. Let me check this one. Okay. This one right here. Oh, are you talking about this reaction? Or let's see. Okay. Let's see. Oh, these ones here. Yep, you haven't learned about this yet. That's at the end of the quarter, 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 end of the quarter. This one you did learn. Um, so
Oh,
out of
okay.
all of
That.
these, you
Mhm.
only need to know how to do this one. The last.
Okay. Okay. I was just like looking at those and I didn't know like they didn't look familiar to me. So
Yeah, yeah. Don't worry
yeah.
about it. Don't worry about this. These.
Okay, yeah. I think I'm just like more confused on I think it was from the first exam that we worked on like last time,
Yeah.
and like they were like the few other problems that we didn't cover, like the nomenclature or like naming them. Like some of them were like very long branches, and then the other one was like a Newman projection drawn form.
Mhm. Okay. Nomenclature, like these questions right here.
Yes.
These questions. Okay. So before we do that, let's do the converting a Newman projection to bond line form
Okay.
um with the stereochemistry. Let's just look at the key. Okay. Okay. Yep. Let's see. We rotate this to that, to that. Yep. Same. Looking down. These are anti. Yep. Eclipsed. Okay. This. That should be anti. Rotate. Rotate. Okay. Draw. Okay. So for this Newman projection right here, let's
Mhm.
convert it into bond line form. We know that this very front carbon that we see is this dot right here. And I'm gonna color code that dot as blue, which is gonna be
Okay.
this blue carbon right here, right?
Uh-huh.
The back carbon right here is going to be in pink, which is this pink carbon right here. And
Okay.
the bond between them, we don't see that, right? Because our eyes are right here,
Uh-huh.
and we're looking down like this, straight on at that carbon,
Right. Okay.
right? And we know that this blue carbon right here is attached to a 1, 2, 3, 4 butyl group,
Yeah, butyl.
right? So I'm gonna
Mhm.
draw that butyl group like this because it's like the most natural for me to draw it this way rather than like this way or like this way, right?
Right.
I just want to draw it right here, right? 1, 2, 3, 4. That's
Mm.
the butyl group. And notice how anti to the butyl group, like on the opposite side of it, is this methyl group right here,
Okay.
right? If I want to make it anti, our reference line is going to be where we are looking at, right? Or our reference line is going to be the bond that we do not see. So I'm drawing that line out
Mm.
to exaggerate where the line is, right? If I want to draw the methyl group that's anti to this butyl group right here, it's
Mhm.
going to be on the other side of the line,
On the other side. Okay.
right? So the methyl group on the back carbon, the pink carbon, is going to be this CH3 right here, which is this CH3 right there,
Okay.
right? And I know it's like that because I know that these two groups are anti to each other, which they are anti to each other like that, right? Now at the front carbon right here, it's also attached to a bromine. So I'm going to draw that bromine as a wedge like this, right? Which makes my hydrogen a dash, but I'm going to leave that hydrogen out as invisible like that, right? I know that's there, but I'm gonna leave it as invisible like that,
Okay.
right? So I know my hydrogen on the back carbon here is anti to the bromine. So
Hmm.
this hydrogen here has to be what if it is anti to the bromine? Like what would it be, wedge or dash?
It would be a dash.
Yes, it would be a dash. But I'm gonna leave that hydrogen as invisible.
Hmm.
So that would make this group a wedge, right? Which is gonna look like this.
Is that because the hydrogen is like on opposite? So like we would say that like hydrogen across from the bromine is dashed, meaning that since it's like semi across from it, we would make it a wedge.
Yes, that's right. Because the hydrogen on the pink carbon here is anti to the bromine, we know that
Hmm.
the hydrogen on the pink carbon has to be a dash because the bromine is a wedge,
Okay.
right? And also, we know that this hydrogen right here on the blue carbon is anti to that group right there. So that makes sense because the hydrogen on the blue carbon is anti to this group on the pink carbon right there,
Okay.
right? So now this is where you would do the nomenclature name. Um, but let me just double check I drew it correctly and check the key for this. Here. So their longest chain is 1, 2, 3, 4, 5, 6, 7. Oh wait, no, I'm missing a carbon. 1, 2, 3, 4, 5, 6, 7, 8, and our substituents are on carbons 2, 4, and 3. Wait, we have a 4 bromo, 2 chloro, 3 methyl, octane. So the stereochemistry here did not matter. They didn't do RS. So you could have just put this as a flat line if you wanted to for this for this exam.
Okay.
Yeah. Uh-huh. But did that make sense on how I convert this Newman projection into this bond line form right here?
Yeah, so just to clarify, like, cause since we can see like the circle is kind of what separates the like what we see from the front and then what we see from the back. So we know like there's a bromine attached to the carbon, a hydrogen, and a um, butane, right?
Yeah, this
So
carbon here.
then
Uh-huh. Right.
we can just visualize like that's the line form that we want. Like
Mm-hmm.
we can already see
Oh shoot. I
as
think
the
am I cutting off or? Oh wait, sorry. What was that? I think you
hello.
you or I cut off for a bit.
Oh, can you
Huh?
hear me? Or is it bad?
Yeah. I hear you now. I hear you now.
Okay. So basically,
Uh-huh.
what we see from the front is like basically the structure that you drew out already. It's just what we see from behind. That
Right.
is what is like that's what's being connected below it.
Yes. So this blue carbon right here that we're looking at, the pink carbon is below it. Right. Like are you talking about the pink carbon here below it or like behind it?
Yeah.
Yeah, that pink carbon is behind this blue carbon right here. So if you're just looking at the blue carbon right here, like that first dot, it's
Mm-hmm.
attached to three groups that we see, right? The
Mm.
bromine, hydrogen, and butyl, right? So ignore everything else. Ignore the pink carbon groups. We see that this blue carbon right here is attached to the bromine, the butyl, and hydrogen like that, right? That's that part of the Newman projection, right? The one that I highlighted in here. The pink carbon behind it, the circle, is this pink carbon right here. We do not see that bond, and we see that this pink carbon is attached to a hydrogen, a methyl, and that group right there, which is this hydrogen,
Mm.
methyl, and that group right there. Notice how these bonds here, like they don't touch the blue carbon. They just stop at the pink carbon
Yeah.
right there,
It's because that's what
the
is
circle.
behind it. Behind
Yeah.
that carbon, which is
Mm-hmm.
attached to another carbon.
Yeah. They stop at that circle. That circle is this carbon right here.
Yeah.
Right. They don't go all the way down like that. They don't touch that blue carbon like that. Right. It's behind it. Right, right.
Okay, that makes sense.
Yeah. Let me give you a practice Newman projection to draw out, and then once you have it, send it to me on Discord, and then I'll move on to Kathy's questions and then Sinyan's questions. Hey Sinyan,
Okay.
how are you?
Good, how are you?
Doing fine, doing fine. How's 118C going so far?
I'm very lost.
Very lost, perhaps.
Yeah, and we have the midterm next week.
Oh shoot, no with no note card allowed.
No, yeah.
Yeah, like Moscow.
Yeah, he said it was unfair to have no cards.
Oh my god. Let's see. Okay. Yeah. Yeah. Try converting this Newman projection out into bond line form. Oh wait, actually let me change this so you can actually name this as well. Let's do this. Okay. Convert this Newman projection into bond line form and name the structure. And then let me know what you get. I don't know what the answer is yet. I just created this like I don't know where, but let me see. Let me know what you get.
Okay, thank you.
Okay. Uh-huh. Okay. So let's see Kathy's question. Uh, Chlorination of alkanes can produce a multitude of products. Determine the number of monochlorinated and chlorinated products that can be obtained by chlorination of 3-methylpentane. Um, consider constitution isomers only. Number of monochlorinated products. 1, 2, 1, 2, 3, 4. Number of dichlorinated products. Okay, so this question here is asking for like if you have this structure and you react it with Cl2 and light, the number of monochlorinated products, like unique products, you got right, which are these four here. 1, 2, 3, and 1, 2, 3, and 4. Right. Why is this not a unique product here? Why did this not count as a unique product?
Because that's the same as the first one.
Yeah, it's the same as the first one, uh, but it's just like flipped over like a pancake, right? Or
Yeah.
or you flip that's a page. You just flip it over, and that's the same thing. So there's 4 unique mono chlorinated products. The other question is asking for how many dichlorinated products are there. So I'm just gonna put some random stuff here. That's one dichlorinated product, right? And I'm gonna make a line like this, and then go from there. This is another one. This is another one. This is another one. And that's another one. So these are the unique ones that I found for this one. Right, let's move on to this one. That's the same thing. This one right here that I just drew out is the same thing as that. Wait. What's going on here? Yeah. This is the same thing as this. This is new. So we are going to have that. This is also new. We can also have this. We can also have this. This right here that I just drew out is going to be the same exact thing as this right here. That's the same thing.
Okay. Oh, it's just flipped.
Yeah, just flipped. Right.
Okay.
Okay, now let's look at this one. This right here is the same thing as this right there.
Yeah.
This right here is the same thing as this. This is new. Right, so I'm gonna draw that in, new one. This is the same thing as this.
Yeah.
This is the same thing as this.
Okay.
Okay, now let's look at this one. This one, same thing as that. This one, same thing as this. This one, same thing as that. This one's new. Oh wait, I just realized that we can have another one like that. So I'm gonna go back and add more. This one is the same thing as that. This one is the same thing as this. Okay, but we could also have this one's here for each one. That one. This one. This one you can't do that. You can't add another coin on that same carbon because that's
Yeah.
gonna break the octet row.
Yeah.
Right? But you can do this. So it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Try 12 and let me know if that works on the achieve homework.
Okay.
Okay. Yeah, so it worked. That's good. Next question, and then let's do 118C. Free radical halogenation can occur with chlorine and source of yep. Chlorination, blah 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 blah. This reaction relative. Okay. Remember the chart I gave you? Did he give you the same reactivity table, or did he use different numbers? Or did the chief give you a table for that?
Which question?
For the second, the last question you sent me on Discord, the
Uh,
percentage, relative percentage.
oh yeah, it says on here, it says primary 1, secondary 3.9, and tertiary 5.2.
Oh, they said 3.9 for secondary and 5.2 for tertiary.
Yeah.
Okay. So we can't use the Levin's table. Let's use the Farhat achieve homework table, because that's different numbers. Okay.
Is it always going to be different numbers depending on the problem, or?
Depending on your professor, the class.
Oh, okay.
Right. Yeah. But for the halogens, they should be different number every time. What's this? I've only seen this or this. I don't know what this is.
One,
So they're asking, this is product A. This is product B. This is product C. Oh, product B, I forgot to do this. Okay. So these are the 3 unique products that you can have. How many hydrogens can, wait, let's just do this. Primary, secondary, tertiary, and this is for chlorine, because we're using chlorine here. You said primary was 1, secondary was 3.9, tertiary was 5.2.
yeah.
So how many hydrogens can create product A?
How many hydrogens?
Yeah.
13?
1, 2, 3, 4, 5, 6, 7, 8, 9,
Oh,
10,
counting
11,
from that.
12.
Oh,
Because if you substitute chlorine with one of these 12 hydrogens, you're gonna create product A.
oh, okay.
Right. So if we have 12 hydrogens,
Mm.
what number do we have to multiply this by if this is a primary carbon for chlorine?
1.
1. 12 times 1 is 12. Okay. How would you calculate the next one?
Would it be 2 times 3.9?
Yeah, because there's 2 hydrogens that could create this product. And because this carbon here is secondary, we multiply that 2 hydrogens by 3.9. Yeah, calculator. I don't know what this is.
Oh, calculate it. Okay.
Yeah. What would this be?
7.8.
7.8. Okay. How many hydrogens can create this product C?
And that would be 2.
Yep. Yeah. There's this one and there's this one, right? That can create that product right there. Okay. 2 times
5.2, which
yep,
is 10.4.
10.4. Yeah. Okay. So these are the relative abundances. To get the percentage, the percent abundance, the total is 12 plus 7.8 plus 10.4. 23.2. Can you double check that? Is that the total?
30.2.
Oh yeah. Wait, 30.2? Oh yeah. Wait. Hold on.
Yeah.
Am I missing something?
Or I'm
19,
using a calculator, so
29. Wait, did I do some weird math? Oh yeah. Oh yeah. This is 2 plus 7, that's 9, 9 plus 10. Oh yeah. What did I just do? Okay, 1 plus 2 is 3, 3 plus 7 is 10, 1 plus 1 plus 1 is 3, 30.2. I don't
mm.
know what I did, but the total should be 30.2. Wait, do you see my updated screen or is it frozen right now?
No, I see it.
You see it? Like you see the 30.2?
Yeah,
Oh, okay.
I
Because
see
for
it.
my screen, it's frozen for some reason. Okay. So, um, the percentage for compound A is 12 over
Mm.
30.2 times 100%. That's the answer. Like you put that in the calculator. The answer for the B is 7.8 over 30.2 times 100%. The answer for C is 10.4 over 30.2 times 100%.
Okay, wait, hold on.
Yeah.
Okay, I got the numbers.
That's good.
Let me check. It still says wait.
Okay, I'm back. Uh, what did you put as the answer? Like, did you put the percentage or did you like?
I put the percentage, but I don't think it's asking for the percentage.
Wait, let me ask. Let me see the question. What was asking for? Relative percentage for this reaction. The relative reaction rates for planners are one. Okay.
Oh
The text.
wait, I'm sorry. I put it on the wrong one. Okay, thank you. It worked.
Yeah, it worked. Okay, that's good. Okay. Hey Zinyan, is there anything that you want to go over for what you can see? Like any reactions, any practice problems, any homework problems you wanted to go over?
If there's no more questions, because I kind of wanted to go over all the carboxylic reactions.
Oh, all the carboxylic acid reactions?
Yeah, so it's a lot, or just the main one.
Let me get water really quick, and then we'll get started on the tables that I want you to know for the midterm. But are
Okay.
you familiar with the reactivities? Like which one's the most reactive and which one's the least reactive derivative?
Not really.
Not really. Oh shoot. Okay, so
Yeah, that's why.
yeah, there's a lot. There's a lot. We'll do the reactions first, and then I'll like explain to you like the reason behind those reactions if you have time for like the next office hours or something. But we'll see. We'll see.
Okay.
We'll do what we can. Because
Okay.
there's a lot. I'm gonna get water first.
Sure.
Uh-huh. Okay, I'm back. So I think what we'll do is I'm gonna explain to you the reactivities of these derivatives and which one's the most reactive and why. And then after that, I'll send you videos to watch for the reactions. And then you can come in with practice problems or questions for office hours next week.
Okay.
So a carboxylic acid is this functional group right here, where we have a carbonyl with a hydroxy leaving group. And I'm going to circle that leaving group in blue because this leaving group here is going to be different for different carboxylic acid derivatives. So when you think of derivatives, don't think of calculus, like there's no math going on here. The derivatives as the groups are deriving from carboxylic acid. They're coming from the carboxylic acid. So I'm going to draw out the derivatives out for you in order of reactivity. The most reactive derivative is if the leaving group is a halogen. Do you functional group name of this derivative, carboxylic acid derivative, where the leaving group is a halogen?
I think you're a little bit delayed.
Oh shoot. Hello. Can you hear me now?
Yeah.
Uh-huh. Am I cutting off still?
No, I think
Uh-huh.
it might have been my problem.
Oh shoot. So to by the leaving groups right here, if the leaving group is a halogen, what would be the name of this carboxylic acid derivative?
Uh, I'm not sure.
Mhm. Yeah, it's okay. It's gonna be right, or you can see this as an acid halide,
Okay.
right? Where X is any halogen, chlorine or bromine, most likely chlorine or bromine. If you have this isolate as a leaving group, then this is called anhydride. Or acyl anhydride. But I think on your homework, they used acid anhydride. If you have an OR group as a leaving group, this is going to be an ester. If you have an amine group as the leaving group, that's an amide. Right. So these are the four main derivatives that you have to know. There is a cousin of this family is trial, right? Because the main derivatives here have a carbonyl or acyl group. The nitrile has no carbonyl, no acyl group, but it's still considered a carboxylic acid derivative because we can convert all of these members or functional groups into the carboxylic acid in one reaction. And that one reaction is called hydrolysis. We could do hydrolysis to convert any of these carboxylic acid derivatives back into the carboxylic acid by using hydrolysis, right? So I'm going to draw out the list out for you more clearly here and explain to you the reactivity of these. The most reactive is the acyl halide, then the acid anhydride, then carboxylic acid is in the middle, which is same or similar to um, an ester, which is going to be more than an amide, which is going to be more than a nitrile, right? So the reactivity of these derivatives are going to increase from left to right. Right, where these are the differences between the derivatives, these leaving groups right here. Right, and then this is a cousin derivative. And the reactivity list here is based on two factors. The first factor is leaving group ability. Right, where if I were to draw out the leaving group of these derivatives, I would have these as a negative charge. Right, where the leaving group ability increases from the same direction as the reactivity direction. Right, and I see that this X minus right here is the best leaving group because the negative charge on that halogen is super stable because halogen is electronegative. But we see here the negative charge on these oxygens right here are the same atom, same electronegativity. But this negative charge right here is more stable than these negative charges on the same atom oxygen because this negative charge here can do resonance with the carbonyl. So resonance is like coming back, it's not going to go anywhere. If it could do resonance, it's going to be more stable, making it a better leaving group. These are similar leaving group abilities, which is why they are similar reactivity. The NH2 minus here is the worst leaving group because the negative charge is on the least electronegative atom compared to the other atoms, right? We have halogen versus oxygen versus nitrogen. Nitrogen is the least electronegative atom compared to those three. So this negative charge here is the least stable on that atom, making it the worst leaving group out of these derivatives. And that makes it the least reactive, right? Because it doesn't want to leave. So instead of seeing leaving group ability, you might see it in the terms of conjugate base, right? Of the conjugate base. Right. Because if you think of leaving group ability, you think of stability. Stability with negative charge, with a negative charge. Back in 118A, we that if something is more stable, it's less reactive. If something is more reactive, right? This one here has the strongest base. That might is the most reactive derivative because the has the weakest base. I don't like to like this. Inversely related reactive you think of like the best or the strongest thing, right? But Farhat, like, in his lecture notes, he said like the most reactive derivative, acer halide, is the most reactive because it has the weakest, which is true. But I don't actually put it because direct to think of it as leaving group ability. I like to say this is the derivative, the best, which makes it the most stable negative charge. And if it's the most stable negative charge, it's the least reactive, making it the weakest conjugate base. Right. Whereas this amide here is the least reactive derivative because it creates the strongest conjugate base. Just leave. Right. Does that factor make sense so far?
Yeah. Wait, did you say the more stable, the more reactive?
The molecule is more stable at peace. It doesn't want to react.
Yeah.
It's happy by itself. It's not gonna be reactive. But the less stable thing is, the more reactive it's gonna be. It's angry, right? It's less stable. It's more angry. It has more energy, so it'll be reactive. It wants to react to something.
So when it's like most stable, it's like weaker as a base, conjugate base.
Yes, yes,
Okay.
yeah. The X minus here is the most stable. That makes it the weakest base. It's
Okay.
conjugate base. Yeah, that's right. Whereas the NH2 minus is the least, making it the strongest base. That's the best factor that drives this ranking list, right? Why one derivative is more like reactive than the other. The other factor of this is going to be electrophilicity. Electrophilicity. Electrophilicity of carbonyl-carbon. Right. So these are the carbonyl carbons that we are looking at. And the bigger the positive charge, the more reactive it is. This has the biggest positive charge because it's the most reactive. This has the smallest positive charge because it's the least reactive. Right, the weakest electrophile. The ones in the middle here are kind of the same. They're similar, so they're in the middle. Right, which is why this second one is not as important factor as the leaving group ability. But the factors that go into the felicity carbon. First one is induction. The other one is resonance. Right, and they're both gonna tie into the electronegativity factor. So a lot of Gen Chem concepts coming back, 118A concepts coming back to describe this ranking list. Right. So if we look at the acyl halide right here, halogen is the most electronegative atom compared to these. So halogen is going to pull or withdraw electrons the most, making that carbonyl carbon have the big positive charge. Another way that's an induction explanation, right? The resonance explanation is this. Halogen has 3 pairs of electrons, but because halogen is the most electronegative atom, it does not want to do resonance with the carbonyl, right? So it does not want to donate electrons into the carbonyl, right? Because halogen is so electronegative, it wants to keep its electrons. So because this carbonyl is not gaining electrons, not gaining positive charge, it's going to maintain that big positive charge. Whereas if we look at the least reactive derivative, the amide right here, nitrogen is the least electronegative, so it has the weakest pull, the weakest induction effect. So it's gonna give this carbon a small positive charge because it's not as strong as a halogen or an oxygen. it's the least electronegative. It's less electronegative than those atoms, right? That's the induction explanation for that. The resonance explanation is that this nitrogen with a pair of electrons wants to do resonance with the carbonyl, right? Because nitrogen is less electronegative than those atoms, it's more willing to give up its electrons and donate into the carbonyl and do more resonance. And if this is doing more resonance, we're giving this carbon more electrons, it's getting more negative charge, which means that it has a smaller positive charge. And if it has a smaller positive charge, it's less reactive, less electrophilic. Did that make sense?
Yep.
Yep. Right. And then oxygen is in the middle. Like do the same explanation for like induction and resonance, but electronegativity of oxygen is in the middle, in between halogen and nitrogen. Right. Okay. So we'll end the session there, but let me check Elysia's work for the nomenclature of Newman projection and convert to one-line form. Have you attempted that yet?
Yeah, but I'm so stuck on it.
Uh-huh.
I mean, I
Oh, you
think,
should suck on.
I can show you what I drew out. It looks a bit crazy.
Uh-huh. Let's see it. Let's see it. Let's see it.
Okay. Let me send it.
Oh yeah. And then when you're sending that, let me send Sinyan the videos that I want you to watch
Hmm.
um to get ready for the midterm.
Okay, thank you so much.
Sinyan.
I watched
Yeah.
your review session.
Oh, you did?
Yeah, I think it was like one from like like your other midterm one review session. That one was helpful
Yeah,
though.
from like the previous quarter,
Yeah.
right? Dang, like that was the one when I did on the whiteboard, like for summer session 1 2024.
I think so, yeah.
Yeah, that's crazy. Did you find that helpful, or because like that
I think I
professor was
did.
that's good, that's good. Different professors though, but same concept.
Hmm.
So good. Okay. I also recorded all the 118B content review sessions that that Zinyan took in
Hmm.
spring 2024. So when you take 118B, those might be helpful to you if um, you take
Thank you.
118B. Yeah, but you're taking Helix, so he's easier than Mescal. So the
Hmm.
stuff that I talk about there like might not be applicable to Helix class. Yeah. Let's see. Okay. Let's see. Okay. Yeah. Watch this these three playlists, Xinyan. These would help you here understand the reactions mechanisms and concepts like base acid properties and chapter 21. Chapter 19, 20, 21. Yeah. Okay. Yeah. And then Kathy, you could find the video on the school um, classroom tab in summer session 1, 2024. My office hours, midterm one review session. Let me actually just send it to you here. And copy. Here you go. Okay, so let's see what you got. Yeah.
Um, I numbered it, but I didn't write down what I noticed like was on there. Um, I can guess what's on the first carbon that you see in the front. Um, I'm not too like I don't have the IU pack like the different purple like like names, but I think I saw a methyl ethyl at the top that is anti to hydrogen.
Isopropyl 1, 2, yep. Bromine, yep. This is the one you don't see. This one is attached to 1, 2, 3, 4. Butyl, nice. This one's attached to this one and an invisible H. Yeah, the trickiest part here would be like determining what group is attached to what carbon. You notice that this hydrogen here is attached to like the back carbon, right? Because it stops there. It stops at the circle. It doesn't go all the way to the front carbon, so that's why that hydrogen is not attached to the front carbon. It's attached to the back carbon
Yeah.
because it stops at the circle.
Yeah,
Yep.
so
So
what's attached to that carbon would be a methyl ethyl, a bromo, and a chloroethyl, I think.
uh-huh. Uh-huh. So yep, something chloro, C2, C2 chloro, right? That's the front carbon that you see. This very front carbon. The back carbon with the
Mm-hmm.
circle is gonna be this one. So you got the structure right. Like this is the correct structure from the Newman projection.
Okay, good. Yay.
Uh-huh. Yeah, yeah, that's good. But let's see the longest chain here. You did 1, 2, 3, 4, 5, 6, 7. But we could have 1, 2, 3, 4, 5, 6, 7, 8 like that. But that's gonna have this crazy complex substituent. So let's see the other way. 1, 2, 3, 4, 5, 6, 7 here as well. Right. So the longest chain is actually gonna be 1, 2, 3, 4, 5, 6, 7, 8. Where
Mm-hmm.
at 4 there's this complex substituent which you would never see on the exam nomenclature. So don't worry about that. Like I just made it randomly. I didn't know it was gonna look like this. So don't worry about
Uh-huh.
the nomenclature for this.
Okay.
Right. Yeah, you get something more doable like the one we did.
Mm-hmm.
Right, like this one
Okay.
right here.
Right.
4 bromo, 2 chloral, 3 methyl octane, something like that. Right.
Mm.
Like you won't get like a long chain like we had 8 carbons and then one of the carbon substituent is very complex. This is one whole complex. Like you won't get that complex substituent.
Right, but I got the structure right.
Yeah, you got the structure right from the Newman projection. This is what the structure looks
But
like.
how would I go by naming it if like I mentioned there was like a methyl ethyl, a chloroethyl.
Uh, if you were to name it, like let's say this was the longest chain right here, but it's not. But then let's say that's the longest chain. These are gonna be our substituents, the ones in blue.
Mm-hmm.
Oh wait. Okay. So our longest chain is heptane. Wait, so this is wrong. Wait, this is the wrong nomenclature. But just imagine, uh, this is a short chain. Okay. We have a 3 iodo. We have a 5 bromo. We have a 6 isopropyl, which is the common name, or you could use 6 methyl ethyl. And because it's a complex substituent, we use parentheses. Um, and then we have 7 chloro. Right? And then we put it in alphabetical order. I'm going to give you 2 names, the common name and then the IUPAC name. The common name is going to be 5 bromo, 7 chloro, 3 iodo, 6 isopropyl, heptane. The IUPAC name is going to be 5 bromo, 7 bromo. I was just singing the ABCs in my head to check the alphabetical order of this. Right. 6 methyl ethyl heptane. Right. So either or would work here, but this is wrong because we don't have the longest chain. But if you were to name it like that, then this is what it would look like with the substituents and base name. Okay. Any questions on this?
I think that makes sense.
Uh-huh. Yeah. Was that your question? Like how you would name these as substituents and the order, alphabetical order?
Um, I guess so. I was like wondering about like the the special names,
Mhm.
like you said, isopropyl or like methyl ethyl.
Right. The isopropyl is the common name. The methyl ethyl is the IUPAC name, the complex
Mm-hmm.
substituent IUPAC name, right? Which is
Okay.
this right here. Isopropyl or methyl ethyl looks like this.
Mm-hmm.
Tert-butyl looks like this. Sec-butyl looks like that. Yeah, common names.
Right. Would you suggest to put that on like the like the mini cheat sheet we're allowed to have during the exam?
Yeah, I would include the common names of substituents on the cheat sheet. Yeah, I would.
Okay.
Yeah. If you can't remember it, then I would do it. But there is a way to remember it though. Like this is isopropyl because there's 3 carbons, 1, 2, 3. That's propyl, and whenever you see iso, it branches out into 2 methyl groups like that. So that's why it's isopropyl. Because there's
Right.
2 methyl groups branching out into a propyl, 3 carbons. Right. This is a tert-butyl because butyl 4 carbons, 1, 2, 3, 4, and it's split into 3 branches. That's why it's tert 3 tertiary. 1, 2, 3 tert-butyl. Right. And then this is a sec-butyl because we have 4 carbons for the butyl, 1, 2, 3, 4, but it's sec
Mm-hmm.
because it splits into 2 branches, secondary, 1, 2 branches.
Oh, okay.
Right. Sec-butyl, tert-butyl, isopropyl. Yeah.
That makes sense. Another quick question. So, for like chlorination and doing those steps, like the initiation, propagation,
Mhm.
um, or would they just be like with methyls that we would be drawing like reactions to, or like the steps, or would it be like, because I don't know what to expect when it comes to those like that portion of the midterm.
They'll give you the reactant, the reagent, the product, and then they'll ask you to draw which part of the mechanism, like initiation, propagation, termination. I have example problems of that, but we could go over them now. Oh shoot, this is the last office hours. But they're just asking you like which part like of the mechanisms to draw out, and then you know how I gave you that general mechanism out when I went over it with you that 1 office hours. You could access the
Yeah, I
notes.
think it was
Um,
bromine.
yeah, like if it's bromine, chlorine, or fluorine, you use that and you react it with whatever alkane they give you.
Mm.
Right. Yeah.
Okay, so it'll most likely be like alkanes and halogens.
Yep. Alkanes and halogens. It can only be alkanes and halogens for free radical halogenation.
Okay.
Yeah. Mhm.
So like for example, the one that you were just hovering over, those ones, like which ones would you point out to be like ones that like would probably be
That you
on?
need to know.
Yeah.
You need to know this. Yeah, the first 2.
Okay.
Yeah. Uh-huh. And these are predicted product questions, not mechanism.
Okay.
Right. Uh-huh.
Okay. Thank you so
Yeah.
much.
Uh-huh. No problem. Okay. Good luck, guys. Are you guys gonna study for OChem now, or what are you guys gonna do now for the rest of the night?
Okay.
OChem or OChem?
Yep.
Oh shoot, everyone's doing OChem. I know. Yeah, I'm so tired. Like I just like I had a long day. I might I don't know. I have a quiz tomorrow though, so I have to like stay up and study for that quiz. I'm gonna take a nap and then study for that quiz.
Good luck for that.
Yeah, and take a power nap. Thank you, Alicia.
What time is your quiz?
My quiz is at 4 p.m. So I do have some time
Mm,
in the afternoon and morning to study for it. I might study for it in class as well, like before that quiz.
mm-hmm.
I don't know what I'm gonna do. Like take a power nap. Uh,
At least it gives
wake
you the
up.
excuse to stay up if you wanted
Yeah.
to.
Uh-huh.
I don't
That's
think that would be a good idea for me because I might miss my exam.
oh yeah. What time is your exam tomorrow? Oh, I'm gonna.
8 a.m.
Wait, it is tomorrow, 8 a.m. Shoot.
Yeah. Yep.
Yeah. Have you
But
guys
good
been
luck.
going to ACC drop-in?
Yes,
Yes.
mm, it's
Crowded.
okay. Yeah,
Yeah.
crowded.
It's crowded. Dang. How do you guys like the? Oh yeah, I asked Elise already. Like you like the renovated basement, but what about you, Zinyan? Like, do you like? How do you feel about that?
Well, I haven't been there like too much. I've been going to
Honest.
co-classes more.
Oh yeah, yeah. Maria Jones
Yeah,
co-classes.
yeah.
Yeah. Is there a co-class for 118A like Maria Jones or Edna Lampson? Like, do they host workshop?
I think Edna.
Edna, yeah, she's good. I did my 118B workshop notes from her, and that's how I used her notes when I did the content review sessions. So Edna is really good.
Oh,
Do you go to Edna's sessions?
no, it overlaps with my schedule,
Oh yeah, yeah, yeah. Dang,
sadly.
yeah. So good luck, Elisa, tomorrow on your midterm. You got it. Work on your note card if you haven't already, and yeah, get some sleep before the midterm too.
Okay, thank you. You too.
Yeah.
Have
Okay.
a good
See you
night.
guys. Good
Thank you.
night.
Bye.
Bye bye. Hi.
And you're still recording?